polynomials. We're going to talk about polynomial functions and their graphs a little bit more, and we're going to talk about how to divide polynomials. So to refresh our memories on the zeros of polynomials, so this is something we learned in 2 lectures ago, last week. So if this is my polynomial, this 5th degree polynomial, it's written out in factored form. I know it's 5th degree because it's got 5 x's all being multiplied together, so my highest degree is going to end up being an x to the 5th. And when you want to find zeros of a polynomial, you set the polynomial equal to 0 and solve. That's actually how you find zeros of any function in general, right? Set the function to 0 and solve. So my zeros, or my solutions to p of x equals 0 are going to be x equals 5, 10, 2, -3, and -7. Take each factor, set it to 0. Okay, so those are the solutions to p of x equals 0. The zeros of the polynomial are the same numbers. The x-intercepts are those same numbers. So if you know solutions to where the function equals 0, then you know the zeros of the function. That's the definition of what a 0 is. And you know the x-intercepts. And the factors we can list as x minus 5, x minus 10, x minus 2, x plus 3, and x plus 7. So we have a special theorem that just says exactly what we have already come to see, that basically all of the following are the same. Okay, so if c is a 0 of the polynomial, x equals c is a 0, then x minus c is a factor. Does that make sense? So because 5 was a 0, that means x minus 5 had to have been a factor. X equals c is a solution to the equation p of x equals 0, and c comma 0 is an x-intercept. So these are ultimately all exactly the same. If you know one thing, then you can come up with 3 other things, right? If I give you a 0, then you know one place where the function equals 0, you know a factor of the function, you know its x-intercept. So if I give you one piece of information, you can come up with 3 more. Okay, so they're all basically the same problem. So I want to use this factor theorem that says that factors and zeros and x-intercepts are all essentially the same thing to decide whether or not x minus 2 is a factor of this polynomial. So basically, I want to know, can I write x cubed plus 2x squared minus x minus 10 as x minus 2 times some other stuff? That's what it would mean for x minus 2 to be a factor, that I can factor it out, so it would be x minus 2 times some other stuff. So if this were my problem, like, how would I figure out if I can do that? If x minus 2 were a factor. What would have to be a 0 if x minus 2 was a factor? 2. I can check if 2 is a 0. That's easy. Plug 2 in and see if it equals 0. Okay, so if x minus 2 is a factor, x equals 2 is a 0. So we check. Do 2 cubed plus 2 times 2 squared minus 2 minus 10. So that's 8 plus 10. 8 plus 8 is 16, minus 2 is 14, minus 10 is 4, which is not 0. Okay, so when I plug 2 in, I do not get 0. So 2 is not a solution to where the polynomial equals 0, which means that x minus 2 is not a factor. that make sense? Okay. So now what I want to do is I want to use the factor theorem again to factor 2x squared minus 3. Okay, so that means I want to write 2x squared minus 3 like that, right? I want to do the double bubble. I want to factor it. So the factor theorem says that if I want to know factors, zeros would suffice, right? If I knew the zeros, then I would know the factors. So maybe if I find zeros, I could just put them in here. I could do x minus, and I'll just write in what the zeros of the function are. So let's find zeros. So I'm going to solve 2x squared minus 3 equals 0. So 2x squared equals 3. Thanks. So x squared equals 1.5, which means that x is what? Square root of 1.5, I don't know. What? 1.23? Okay. Plus or minus 1.23. Right? Square root both sides, you gotta do plus or minus. So I have two zeros, positive 1.23 and negative 1.23, which I could also write, that's approximate. If I wanted it to be exact, I would say square root, the square root of 3/2, right? Or the square root of 1.5. So I'm going to do x minus the square root of 3/2, and then x minus negative square root of 3/2, so plus. Now, when you FOIL that guy out, what's the leading term going to be? That's what I want it to be, right? But when I FOIL this, you just get x squared. We're missing the 2. Throw it out front. Just carry it along. So if you can find zeros, you can find factors. If you can find factors, you can find zeros. All right, so we have a few different ways to find zeros. We can use a quadratic formula, but that only works for quadratics. We can find zeros by our graphing calculator, and we can find zeros by factoring, but that's harder as the degree gets higher. That gets harder and harder to factor. So what if I wanted to find the zeros of x squared minus 8x plus 4? Which one of our methods would you use? Factoring or the quadratic formula? Yeah. If it doesn't factor, so you might try factoring first, and if it doesn't factor, you resort to the quadratic formula, right? Quadratic formula, which says that x is negative b plus or minus the square root, which, now that we've had some practice with it, seems like a relatively simple, straightforward formula to use. But, you know, when we first learned it, it's a little complicated, deciding what's A, what's B, and what's C, and getting the signs right. So it turns out that there's a comparable formula for cubics. If you want to set a third degree polynomial equal to 0 and solve, there is a formula. And I don't have it. But you have it in your papers, right? Yeah. So this big monstrous thing, you were not going to use it. But just so you know, it exists. So instead of using that intimidating, monstrous formula for a cubic, we're going to try a graphical / algebraic approach. We're going to do both. Okay, so if we graph this function on our calculator, we're going to find 3 zeros. That's 3 x-intercepts. So clear anything that's in there. All right, so x cubed minus x squared minus 24x plus 48. I'll use just a standard window, zoom 6. We have 3 x-intercepts. Okay, so 3 zeros. One of them looks like it goes right through a nice, integer number. This one on the far right looks like it's 1, 2, 3, maybe 5. I don't know, it's hard to tell. Maybe 6, 4. It's 4. Okay, so we can calculate it perfectly. Have the calculator do it and go to the calculate menu, choose 0. We have to give a left bound. And a right bound. And a guess. And you get x equals 4. Okay. So one of them goes through a nice whole number. So it looks like 4. We can double check it. Or if instead of having the calculator find it, if we just looked at that and said, oh, looks like 4, we could check by going to our table, plugging in 4, and seeing if we get 0 for y. Okay, if that happens, then you know that it's definitely a 0. So x equals 4. Okay, so now that we have one solution, we're going to find the other two algebraically. So we use our calculator to get the nice one. We could use the 0 command on our calculator to get the other two, right? I could do the exact same thing as I did for this one. But the problem with that is that it's only going to give us an approximate answer, right? It's going to give us a decimal because they're not nice whole round numbers like 4 is. So it's only going to give me a decimal approximation. And it would only work in this case because the other two x-intercepts happen to be in the viewing window. If they didn't happen to show up in there, I wouldn't even know that they existed. So I get 1 from my calculator, and then I can do a nice little algebraic trick to get the rest. All right, so since 4 is a 0, what do I know has to be a factor? X minus 4. X equals 4 is a 0, which means that x minus 4 is a factor. So if I had this thing all written out in factored form, and I've got it like blah, 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 right? And I know that x equals 4 is a solution. That means that x minus 4 had to have been a factor one step earlier. All right. So x minus 4 has to be a factor. So here's a little aside. We're going to just talk about division of numbers for a minute, and then we'll bring it back to polynomials. So we're going to try to remember what it means to be a factor. So if 22 is a factor of 2,970, what does that mean to you if I say that 22 is a factor of 2,970? Yeah, I can write. Yes, so there's two ways to think of it. I can say I can take 2,970 and divide by 22, and I get some whole number, right? It goes in an even number of times. Or I could think of it as that means that I can write 2,970 as 22 times something, right? If I multiply both sides of this equation by 22. So that's what it means to be a factor. If 22 is a factor of 2,970, that means I can write 2,970 as 22 times something, times some other stuff. Okay. So if x minus 4 is a factor of this polynomial, that means you can write this polynomial as x minus 4 times some stuff. You can write it as a factor. Okay, so I've got my polynomial x cubed minus x squared minus 24x plus 48. I know x minus 4 is a factor, which means that I can write my polynomial as x minus 4 times some other stuff. So the question is, how am I going to find this other stuff? Got a polynomial is equal to x minus 4 times something unknown. How could I figure out what that unknown stuff is? Yeah, divide both sides by x minus 4. So over here, these cancel. And we have that the stuff that we're looking for is the quotient of x cubed minus x squared minus 24x plus 48 divided by x minus 4. So now it becomes important to say, well, how do we divide two polynomials? We can add and subtract and multiply them. We've done all that before. When you add, you just combine like terms. When you multiply, you distribute. So now the question is, how do we divide these? All right, so without a calculator, we're going back to our little aside. I want to write 2,970 as 22 times something. What is that something? How do I figure out what it is? Yeah, divide 2,970 divided by 22. Okay, and if I say that you can't use a calculator, we're going to have to do long division. So we're gonna have a little review of elementary school for a minute. Okay. So remember, we're working in base 10 here. Okay, so I say we look at the 22, and we only look at as many leading terms as we have to, right? As many of the leading digits as we have to. So digits correspond to terms of a polynomial. So each digit of a number is like a term of a polynomial. So I only look at as many leading digits as I need to, and until I get my divisor something that it can go into. So I'm looking at my 29 here, and I say 22 goes into 29 how many times? Once, so you put the 1 right here. Okay. And then you multiply 1 times the 22, you get 22, and you subtract. 29 minus 22 is 7, and then you bring down the 7 next to it. Then you say 22 goes into 77 how many times? 3. Put the 3 there. 3 times 22 is 66. So we get 11, bring down the 0. 22 goes into 110 5 times. 5 times 22 is 110. You subtract. And once you get this 0 here, then you know you're done because that's the remainder, right? Once you get a number smaller than 22, you're done. And if it's a 0, it went in evenly, right? So we know that 2,970 can be written as 22 times 135. All right, so polynomial long division works exactly like long division with numbers, almost. So if you can do this, you can do polynomial long division. Just have to make a couple small adjustments. Oops. All right, so I'm going to divide. Actually, I'm going to do it on a separate slide so I have enough room. X cubed minus x squared minus 24x plus 48. I want to divide that by x minus 4. So go back to the numbers for a minute. The 2 and the 9 didn't really matter here. What I really was looking at was the leading digit on my divisor and the leading digit on my number I'm dividing into, right? So the 2 goes into the 2 once. So really all that mattered was the leading digits. Same thing here. And then also, when you ask how many times does 22 go into 29, you're really asking what can you multiply 22 by to make 29, or as close to a number as 29 as you can get. All right. So I'm going to say, how many times does x, I'm just going to look at the leading term of the divisor and the dividend. And I'm going to say, how many times does x go into x cubed? That is, what do you multiply x by to make an x cubed? X squared. So I'm going to say, okay, x goes into x cubed, x squared times, and I'm lining it up with the term that it's like. Right? So I do that with the numbers also. I lined it up with its place value. When I said 22 into 29, I was really dividing 22 into 2900. And the answer was 100, so I put the 1 in the hundreds place. All right. Now I do the same thing as I did with long division with numbers. I take my x squared and I multiply it times this divisor. So you do x squared times x, which gives you x cubed, and x squared times negative 4, which gives you negative 4x squared. So you multiply that x squared times the whole divisor. Then you subtract. So x cubed minus x cubed, those go away. Leading term goes away. And then we have negative x squared minus negative 4x squared. So what is x squared minus negative 4x squared? 3x squared, right? 1x squared plus 4x squared is 3x squared. Then bring down the negative 24x. Then we just do it again. And you ask yourself, what should I multiply x by to make 3x squared? 3. 3x, right? 3x. So I put a plus 3x up here. And then you multiply your 3x times your x minus 4. So you do 3x times x, which is 3x squared, and 3x times negative 4, which is negative 12x. Then you have to subtract this whole expression that we just wrote down, subtract the whole thing, so I add parentheses. So 3x squared minus 3x squared, those go away. Then you have negative 24x minus negative 12x. Negative 24 minus negative 12. Negative 12x, yep. And bring down the plus 48. And then we just do the whole procedure again. You say x times what would give me negative 12x? Negative 12. And then you take your negative 12 and you multiply times the x minus 4. Negative 12 times x is negative 12x. Negative 12 times negative 4 is positive 48. And then I subtract. So negative 12x plus 12x, those go away. 48 minus 48, those cancel. I get 0. Okay, so my remainder is 0. And my answer, right, when I divide the cubic polynomial by the x minus 4, I get x squared plus 3x minus 12. So it will take a little bit of practice. Once you do it a few times, you'll start to really feel the similarity with regular long division. Okay, so now I can find all the zeros because I can write p of x in completely factored form. So p of x, which is x cubed minus x squared minus 24x plus 48, I now know can be written as x minus 4 times my answer here, x squared plus 3x minus 12. And can x squared plus 3x minus 12 factor? I don't think it can, yeah. So that is fully reduced form. We haven't talked about, okay, no, never mind. All right, so that is not quite done. I can still get my quadratic to be written as two linear terms, product of two linear terms. And the question is, what are they? So I've got two unknown linear terms. I can use my factor theorem to find them, because if I know the zeros of that thing, then I'll know its factors. So I want to find the zeros of x squared plus 3x minus 12. So I set x squared plus 3x minus 12 equal to 0, and I would solve it with the quadratic formula, because it doesn't factor. So I get x equals negative 3 plus or minus the square root of 9 minus 4 times 1 times negative 12 all over 2. So this is negative 3 plus or minus the square root of 4 times 12 is 48, and 9 plus 48 is 57. So negative 3 plus or minus radical 57 over 2. Those are my two zeros of this quadratic, which means that my factors are x minus negative 3 plus radical 57 over 2, and negative 3 minus radical 57 over 2. So if I have two zeros, I know two factors, just x minus each zero. So I'm going to have x minus negative 3 plus radical 57 over 2. And x minus my other zero, negative 3 minus radical 57 over 2. So now I've got my cubic written in completely factored form. 3 zeros and 3 factors. Okay, so the last thing for this lecture is to talk about multiplicity of zeros. Okay, so x-intercepts are zeros of a polynomial, right? They're essentially the same thing. But you might notice that there are different kinds of x-intercepts. Some x-intercepts bounce off the x-axis. Some intercepts go right through the x-axis, cut straight through like a knife, right? And some go through the x-axis, but they kind of take their time passing through. It kind of looks like they are stalling, right? They're lagging behind, and then they go through finally, and then they finally leave. So there's sort of three flavors of x-intercepts. Bounces off, goes right through, and takes its time going through. So if I were to zoom in on each of these, okay, so what we can take away from this is that when the polynomial bounces off the x-axis, zooming in on that x-intercept looks like an even degree polynomial. That's what we call even multiplicity. An even multiplicity. And when the graph crosses the x-axis, we call it odd multiplicity. And if it looks like a line, it's multiplicity 1. And if it kind of flattens out and stalls on its way through, it's odd but bigger than 1. So like 3 or 5 or 7. And what multiplicity means is the number of times the zero occurs, right? So if I was trying to find the zeros of this polynomial, I would do x plus 3 times x plus 3 times x minus 2 times x minus 2 times x minus 2 times x minus 4 equals 0. So I just wrote out x plus 3 times x plus 3 instead of x plus 3 squared. And x minus 2 times x minus 2 times x minus 2 instead of x minus 2 cubed. And then when you're solving something like this, you take each factor and set it to 0. So I would set x plus 3 equal to 0 twice. And I would set x minus 2 equal to 0 3 times. And x minus 4 equal to 0 once. So that means x equals negative 3 is a 0 of multiplicity 2. Because I had two equations that when I solved them, I got x equals negative 3. X equals negative 3 is a 0 of multiplicity 2. And when I end up graphing it, I end up getting what looks like a quadratic. I get a bounce-off effect at that particular 0 at negative 3. And when I set x minus 2 equal to 0, I do that 3 times. I get x equals 2. So we say that that 0 has multiplicity 3, because I got that as a 0 3 times. Okay. And when you have odd multiplicity, you get this kind of, it goes through the axis when you have odd multiplicity. But if it's odd and bigger than 1, it goes through and kind of like flattens or stalls as it goes through. And then my last factor, x minus 4, set that to 0, I get x equals 4. I only had one factor of x minus 4, so x equals 4 is a 0 of multiplicity 1. And a multiplicity 1 is going to go right through the x-axis like a line. So that would be this 4 over here. So let's take a look at this graph here, and I want to come up with a possible equation. It's not necessarily the only equation, but based on what we know about zeros and multiplicities, we'll come up with a possible equation. So let's see, for zeros, I've got negative 2, 0, and 1. Those are my three x-intercepts. So x equals negative 2. What kind of multiplicity does that look like? Odd. And does it look like 1 or bigger than 1? Does it go straight through like a line, or does it kind of stall? It's greater than 1, yeah. So we'll say 3. Now this part is a guess, right? If we just know it looks like it's bigger than 1, we'll choose 3, because when you're making up equations, why make it harder than you have to, right? So 3 would be the easiest. So we'll say multiplicity 3 for that one. And then I have another 0 at x equals 0 right here. Does that look like even or odd? odd. It goes right through, so it's odd. It goes through the axis. And it goes through looking like a line, which means what's my multiplicity? 1. And then finally, I have x equals 1. What would the multiplicity of that one be, even or odd? Even, because it doesn't bounce off. It looks like a quadratic, so it's got to be even. The smallest even degree would be 2. So to keep things as easy on us as possible, we'll say it's multiplicity 2. It could be 4 or 6 or 8, right? But I'm going to make the smallest polynomial possible. Okay, so if these are my zeros, then I know my factors, right? If x equals -2 is a 0, then I know that x plus 2 is a factor. And because it's a 0 of multiplicity 3, it's going to be a factor 3 times. And then x equals 0 has multiplicity 1. So if x equals 0 is a 0, that means that x minus 0, or just plain old x, is a factor. Multiplicity 1, so I just do it once. And then if x equals 1 is a 0, that means x minus 1 is a factor. And because it's multiplicity 2, it's a factor twice. And then if you want, you can use exponents to write this in a shorter way. Do x times x plus 2 cubed times x minus 1 squared. Is that okay? All right, so I am going to have you work for a little bit in your groups on this activity, factoring polynomials.